Hello students, parents, family, and community members. I'm Dr. Kelly Baudo, Assistant Superintendent for the Buffalo Public Schools Division of Curriculum, Assessment, and Instruction. It is my pleasure to introduce you to the BeEnriched television initiative, where students will have the opportunity to participate in instructional lessons and virtual field trips. The program is designed for students in the Buffalo area from kindergarten to grade 12, and the instructional lessons are designed and delivered by Buffalo Public School teachers. The lessons support literacy, history, STEM education, and the arts. Culturally responsive lessons will be included along with virtual tours of Buffalo's cultural institutes and landmarks. There are a total of 40 half-hour segments. It is our hope that you can tune in every day, Monday through Friday, to immerse yourself in these learning experiences. If you miss a class, no worries. We will be repeating these throughout the next several weeks. Also, each course and description will be archived and can be viewed at any time on BeEnrichedBuffalo.org. We would like to thank the people who have made BeEnriched possible. Those include Harmac Medical Products, the Community Action Organization of Western New York, and Key Bank in partnership with First Niagara Foundation. Without the three organizations, this programming could not be possible. Additionally, we would like to thank Buffalo Schools Superintendent Dr. Kreiner Cash for his commitment to the students and families of Buffalo, ensuring that there was support for the BeEnriched program. We would also like to thank Dr. Darren Brown Hall, Chief of Staff, Ms. Ann Botticelli, Chief Academic Officer, and last but certainly not least, the dedicated school teachers who have prepared and taught the enriched lessons. Thank you and enjoy watching these special shows.
Hello and welcome. My name is Stephanie Finn. I'm the Buffalo Public School District Science Department TOSA, or Teacher on Special Assignment. I work for the Department of Curriculum, Assessment, and Instruction, and today we're here to talk about and learn about convection currents. Now, convection currents can occur naturally or they can be man-made. We're going to find out more about that today. I want you guys to think about this for a minute. Have you ever noticed that it's warmer on the second floor of your home or in your attic than in the first floor or your basement, especially in the summertime? Have you ever wondered how a hot air balloon stays in the air? Have you ever wondered why smoke rises from a fire? Or have you noticed how water boils in a pot and the pattern of how the water is boiling in a pot? All of these questions will be answered in this segment today. First of all, what is convection? Now, convection is the transfer of thermal energy by the motion of matter at different temperatures. And we're going to model that today with the experiment that I have set up for us. What is a convection current? A convection current transfers heat from one place to the other by a mass motion of fluid. Now, a fluid can be water, a fluid can be air, or a fluid can be melted rock. When we see convection currents in water, we might think about the ocean, or we might even think about that simple pot of boiling water. When we think about air motion, we might think about our example of it being warmer in your house on the second floor or the attic than the first floor or your basement, or even in weather patterns. And when we think about melted or molten rock, we think about plate tectonics. Convection currents drive the ocean currents, the atmospheric weather, and Earth's tectonic plates. Why does this occur? This occurs because heated fluid expands and it's less dense. When something is less dense, it rises in either the air or the medium that it's in. As it rises, it pulls that cool air down to replace it. This creates a cycle or a circular motion or current that actually stops when all of the heat or thermal energy is evenly distributed throughout the fluid or closed condition that it's in. So today what we're going to do, boys and girls, is I have two setups. We're going to set up both of these. If you notice, I have a cup inside a mini cup, or a mini vial inside this cup. There's two holes here. Both of them are equally the same. In the first cup, we're going to put warm water here. It's going to be red. And we're going to surround it by cool water. And we're going to see if we can create a convection current, meaning that the warmer water in the bottom of this cup in the mini vial is going to want to rise. We're going to see if we can get that to happen. In this cup, we're going to do the exact opposite. In this cup, we're going to take the cooler water, and it's going to be colored blue. We're going to surround it with warmer water that's going to be clear to see if we can create a convection current when there is cooler water in the bottom surrounded by warmer. We're going to see which model creates the best convection current. Welcome back, folks. Now we're going to get ready for our demonstration of convection currents, and we're going to see which model creates the best convection current. As I explained earlier, I have this cup, and inside the cup is a little mini vial with two openings. Same setup. In this cup, in the mini vial, we're going to put warm water that we colored red. We're going to surround the warm water with cooler water. We're just going to pour it in. We're going to see if we can create a convection current. Then we're going to do the opposite in this cup. In this cup, we're going to put cold water in the little mini vial. The cold water will be blue. And we're going to surround it by warm water. We're going to see if that will create a convection current. All right, so I'm going to take this syringe, and I'm going to fill the syringe with the warm water, and we're going to fill up the mini vial. Okay. Now I'm going to take the cooler water, I'm going to use my finger, and I'm going to cover the two openings in the mini vial, and I'm going to surround it with cold water. If we create a convection current, the warmer red liquid is going to want to rise above the cooler water. Remember, the warmer water is less dense. It's going to rise, creating our current. All right. So we can see the warmer water is rising. It's actually up on top here. And if we give it a few minutes, the water will begin to cool up on the top, and it'll start to sink. Now if I had a heat source, if this were a stove in the bottom of this, what would happen is I would be creating a circular motion like when you're boiling water. But I don't have a heat source here. I just have the warm water in the bottom so that you can see that's creating that the warm water is escaping through the openings in the mini vial. The warm water is lingering at the top of the cup. As it cools, we should be able to see it falling. All right. So what we're going to do now is we're going to do the exact opposite of what we did here. we're going to be putting cool water at the bottom of this mini vial, in the mini vial, with the syringe. We're going to surround it with warm water, and we're going to see if that cold water will rise to the top as the warm water did in this model. So I have my cold blue water here. I'm going to fill up my mini vial. My warm water is going to be clear for this one, so we can see if there's any movement of the colder blue water. Okay. Let's see if it's going to move. Alright, so I made a little bit of the cold water escape out of the mini vial, but you can see that none of the blue water is coming out of the mini vial. It's colder water, and it's not rising to the top. It's being contained because it's being surrounded by warmer water, so we're not creating a convection current here. Over here with this one, we've created a convection current. The warmer water was at the bottom of the cup. We surrounded it with colder water. The warm water rose out of the mini vial, surrounding the colder water. And you can see where it's starting to fall down. Now we got some condensation here going on, boys and girls. Let's try to get rid of that so you can see that that red water, the warmer water, is cooling at the top of the cup, and now it's falling back down, or it's becoming more dense. And as it becomes more dense, it's losing kinetic energy because it's cooling, and it's drifting down to the bottom of the cup. And here we still have our cooler water that we colored blue. In the bottom of the cup, it's surrounded by warm water, and we don't have any movement. So we've created a convection current here, but no convection current was created with this model here. So we can say that the warmer fluid or water rose to the top surface. As it cooled, it's starting to go back under. As the water temperature starts to combine to create one temperature of the water, eventually what we're going to see is we're going to just see this all turn red because the temperature will start to equalize out. So when we come back, we're going to see some real-world applications of this. Real-world applications of this include weather currents. It includes the movement of our plate tectonics. And again, hot air balloon. If you've ever seen a hot air balloon, this is why a hot air balloon rises, that the air in the hot air balloon will rise. And then once they cut off the heat for that warm hot air balloon, it'll start to drift down. And again, on that hot day in Buffalo, New York, when you go to your second floor, it's warmer. When you go down on your first floor in your basement, it's nice and cool because you're experiencing warm air rising and cool air remaining below the warm air. All right, welcome back, boys and girls. Whew, on these hot days in Buffalo, New York, have you ever just wanted to go down by Lake Erie or down by the Niagara River and want to feel that cool sea breeze or lake breeze coming in? Well, this graphic and what you've learned from our convection currents will explain to us why we feel so much cooler when we're down by Lake Erie or down by the Niagara River. So we have our land here, and this is our heat source, and the land is heating up the air. Oh, can we?
Let's start again.
Yeah.
That was fun.
Oh, you know what? It's a smart board, and I touched it.
You touched the snake.
I touched the smart board. I'm sorry.
I'll wait till it comes up to 26 minutes.
Okay.
For my clock. So about 10 seconds. 4, 3, 2.
Welcome back, boys and girls. Whew, it's been a hot summer in Buffalo, New York, and I'm sure everybody has wanted to go down by Lake Erie or down by the Niagara River to get those cool sea breezes so we could cool off and relax. Well, what we're going to learn in this picture and what we've learned from our convection current models will explain why we feel so much cooler when we're down by the water. So, in this picture, I'm going to explain the arrows, and these arrows would demonstrate the convection current. So, we have our lake, and I know this says sea here, but we're going to pretend it says lake. So we have our lake, or we have our river, our large body of water, and we have our land, and it's so much warmer on the land or in our house than it is by the water. The warm air is rising. As the warm air rises, this help forms clouds. The wind is moving the air over the water. The air cools, and as it cools, it's sinking. The sinking air gets blown across, the cooler air gets blown across, creating a sea breeze. So we have a nice convection current started here, where we have our heat source of the land. It's rising. The air is going to move over our cooler water surface. It sinks because it's cooling, and then the wind is going to blow that back over the land. So this is why when you go down to the lake or the river, you have that nice sea breeze cooling you off and making you feel a lot more comfortable. The opposite happens in the evening, where the water is warmer than the land. So if we were to take the arrows and reverse them, the wind would be blowing in this direction because the water would be warmer than the air. That's why when you go into a pool late at night, it feels warmer because it's warmer than the air at that point, and you get a nice land breeze. So this explains sea breezes and land breezes with the convection currents that we've modeled here. I also want to show you a nice video clip of hot air balloons. I've talked about hot air balloons a couple times here, and how the only way they can get into the air is if they are heated. So you can see we have a flame here heating this hot air balloon. We're going to take a look at this video for a few minutes so you will be able to see how a hot air balloon works. So you can see the flame right there heating the air. It's a closed system, so that warm air is surrounded by the colder air of just being outside surrounding that hot air balloon. They need to have that heat source right here heating up that air that is going to be contained in that hot air balloon. And you can see our hot air balloons are all floating in the air. So again, that's our heat source. You can see the heat source right here is heating up the air that's contained in that hot air balloon. The surrounding air outside the hot air balloon is cooler, so that's going to force the hot air balloon to go up into our atmosphere and float. Okay. One other thing we talked about with convection currents are plate tectonics and how our plates move. Remember, when our plates move, we might get an earthquake or a volcano. So, in this plate motion simulation, we're going to be looking at a few different ways our plates move. And plate movement is partially caused by convection currents that we've modeled here. We're going to talk about how two continental land masses converge, move towards each other. This is from the convection currents. How an oceanic and a continental plate will move towards each other. How two continental plates move away from each other. And how an ocean plate and a continental plate move towards each other. All driven by the force of the melted rock, and the melted rock is driven by the convection current. So the first one we're going to look at is a convergent plate. And this is where the continental lithosphere is moving towards each other. Now I just want to explain what this legend means. The continental lithosphere is this lighter gray, you can see right here, and the arrows are moving towards each other. Oceanic lithosphere is not here. We don't have ocean. This is continental lithosphere. We have our mantle here, and this is our molten rock. This is the driving force. This is where the convection current is. It's going to be making these plates move. We have a GPS station. The three circles inside each other are a symbol for an earthquake. This green hump is a mountain. This gray upside down triangle is a volcano. Then we have an underwater volcano. The blue line is a river, and the red line could be an abandoned riverbed. So what I'm going to do is I'm going to pick a time of 20 million years. And we're going to see what occurs on the Earth's surface over the course of 20 million years. Now I want you to remember that this is the mantle, and the mantle is what has a convection current in it. The mantle is being heated from the core of the Earth. That warmer mantle or melted rock is rising very slowly to the surface, which is creating this movement of the continental lithosphere. So we'll see what happens in 20 million years. So you can see those continental lithospheres moving together. Mountain ranges are forming. The mantle is convecting. Now if we want to see the same thing when the continental lithospheres are moving away from each other, we're still going to have a convection current because that is what is driving the motion of the continents or the continental plates. All right, you can see that this plate is being pulled apart or dividing or diverging. The lithosphere is moving. We have earthquakes and underwater volcanoes forming, and actually small islands forming. This is all driven by the movement of the mantle, and it's moving because of convection current. The third one I want to show you is what happens when an oceanic plate moves towards a continental plate. So here's your continental plate, continental lithosphere, lighter gray. The oceanic lithosphere, the darker gray. You have your mantle underneath, and remember the mantle is experiencing a convection current. I'm going to pick 20 million years. Lots of earthquakes. And again, this is from the convection current in the mantle. So we have mountain ranges forming, volcanic mountains forming as well. Now we're going to see what happens when two oceanic plates move towards each other, or they're converging on each other. Okay, the plates are moving towards each other. These are two ocean plates. We have lots of earthquakes and volcanoes forming, and again, it's due to this convection of the mantle or the melted rock underneath the tectonic plates of the earth. So, if we review, why is it warmer on the second floor of your home or your attic than the first floor of the basement? It's due to a convection current. How a hot air balloon stays in the air? Due to a convection current. Why smoke rises from a fire? So that less dense, warmer air is moving up, and we can see the dust particles in the smoke. We can see that. And then if you ever noticed how a pot of water boils, the heat source is that stove, and the water is warming and rising to the surface. Okay, boys and girls, well, today we have studied convection currents. We've seen how it related to plate tectonics, the nice breeze that we feel along the Lake Erie or the Niagara River, and why it is cooler in our basement or first floor, especially in the summer. I want to thank you all for tuning in. If you have any other questions regarding convection currents, please don't hesitate to ask your science teacher. I want to thank you for this opportunity, and let's go science.